Okay, we're going to do a power series for f of x equals square root of x centered at c equals 9. If you've tried one of these, the power series for the square root function centered really anywhere is actually one of the trickier power series to write a formula for using Taylor's formula. So I wanted to show you how to do that. So, and there's actually two techniques for writing the series for this one. So we know Taylor's formula says I want the from n equals 0 to infinity, the nth derivative evaluated at 9, because that's my center, times x minus 9 to the n over n factorial. And the challenge is going to be finding a formula for the nth derivative at c equals 9. So we'll start taking some derivatives. That's how we've been doing it. And we're searching for a pattern. And as we've seen, searching for a pattern, you want to not simplify. Don't simplify so you can see what's happening each time you take a derivative. So we have x to the 1/2 x to the negative 1/2. When I bring that negative 1/2 down, I'm going to put it next to the 1/2. So I get that. And when I bring the negative 3/2 down, I'm going to put that next to the x. And then the next one, the negative 5/2 comes down. And we can start to see a pattern with the powers. You get this sequence. The original 1/2 is there, and then we have -1, -3, -5, -7, and of course the next one there would be a -9. So we have consecutive odd numbers getting multiplied together. Okay, so the trick is, how do I express that? Let me go back to the third derivative and let's just see if we could simplify this. So the way to deal with it, we don't do factorials or any kind of thing with negative numbers. So those, but we can handle each of those negatives as like a little -1. So if I have two negatives, I can think of that as -1 squared, and then I have 1 times 3. And my denominator would be 2 to the third, x to the negative 5/2. If I go to my fourth derivative, there's 1, 2, 3 negatives. I can think of that as -1 to the third. And then the pattern I have is 1, 3, 5. X to the negative 7/2 over 2 to the fourth. Same thing on my fifth derivative. Notice there are 4 negative ones. 1, and then they have the pattern 1 times 3 times 5 times 7, x to the negative 9/2 over 2 to the fifth. So the challenge is writing this formula for the pattern, 1, 3, 5, 7. Okay, so there is a way, there are a couple of ways to, actually 3 different ways to express it, which I'll show you. I mean, one way to do it, and I think this is the way, if you happen to have an odd number problem, the way the back of the book would provide their solution. One way is to just describe the pattern, 1, 3, 5, ... and you want to tell somebody, you want to have a formula on when you should stop. Okay, so using my fifth derivative as an example, I want to multiply the numbers 1, 3, 5, and 7. They're skipping by 2, and we know a formula to skip by 2 would be a 2n. On my fifth derivative, I want to stop at 7. So when n is 5, that would give me 10. So if I subtract 3, that would give me the correct number to stop on my fifth derivative. It would be 7, 10 minus 3. And of course, that works on my fourth derivative. If I plug in 4 there, I get 8 minus 3 is 5, and that's where I want to stop. Okay. So you could write it as 1, 3, 5, ... 2n minus 3, this pattern right here. Another notation that does exist, you can look this up, is little known, but it's double factorial. So we know how factorials work. You start with a number and you subtract 1, keep multiplying down until you get to 1. N double factorial is known or understood to skip numbers all the way down to 1. And it's just understood that if you started with an odd number, like 5 double factorial would be 5 times 3 times 1. You would use the odd numbers, so it'd be n minus 2, n minus 4 if n is odd. And if you happen to start with an even number, 6 double factorial would be 6 times 4 times 2. Okay, you would be skipping a number here. So 1 times 3 times 5 times 7 could be expressed as 7 double factorial. And that pattern we have right here could be expressed as -1 to the n minus 1. Notice, remember on my fifth derivative, I had 4 -1s, so I'd have -1 to the n minus 1. I could express this pattern here as 2n minus 3 double factorial. The denominator is 2 to the n. I have 5 powers of 2 on my fifth derivative. And then a formula for -9/2, that would be -2n minus 1 over 2 would give you the correct number. So that would work. Condense down. Yeah, remember you have to plug in your nth derivative evaluated at 9. All you do is replace your x with 9 to the -2n minus 1 over 2, and that could go to the denominator, right? I've just brought it down. So all of that is a formula for my nth derivative evaluated at 9. Okay. Now another, or I should say this, or you could either do this notation, or you could write, in place of the 2n minus 3 double factorial, you could write 135 ... 2n minus 3. So you could put this right in here. That would work too. That's fine. Now there's a dilemma with this, is that this pattern, this 1 times 3 times 5 times 7 pattern, I'm going to slide this back up. This pattern that we had so much trouble writing a formula for, if you trace it back to its origins, 1, 3, 5, 1, 3, 1. The pattern started actually on our second derivative, right? It didn't happen for our first two powers. So what the repercussions of that is, we can write this formula from 2 to infinity, and what we have to do then is write the first two terms separately. Remember, the first two terms of a Taylor series are f of c plus f prime of c times x minus c. So the correct representation would be these two terms plus this series from 2 to infinity. Now, it has come to my attention that if you're doing this on WebWorks, for example, WebWorks does not recognize the double factorial notation. So if that's the case, there's another way, yet another way you could write this pattern that we were working on, 1, 3, 5, 7 to 2n minus 3, which we were writing as 2n minus 3 double factorial. It just so happens that you can express let's start with 1 times 3 times 5 times 7 can be expressed as 8 factorial divided by 2 to the 4th times 4 factorial. And what I just said here is try it. Write this out. Write those all out. And then 2 to the 4th and 4 factorial. And you'll be able to divide a bunch of stuff out, and you'll be left with this. Similarly, 1 times 3 times 5 times 9, 5 times 7 times 9 can be written as 10 factorial over 2 to the 5th times 5 factorial. The product of the odd numbers all the way to 11 can be written as 12 factorial over 2 to the 6 times 6 factorial. So this will work. You can see a pattern here. So if I wanted to go 1, 3, 5 all the way to 2k minus 3 or 2n minus 3, whichever one I switch to k for whatever reason, you could write it as 2k minus 2. You're going to go one further here, okay, factorial over 2 to the k minus 1 divided by k minus 1 factorial, or n minus 1 factorial. So this should work. This should work. WebWorks should recognize this because it has no trouble recognizing single factorials. It just has not been programmed to understand what double factorials are. Now, personally, I think what I would have, if I had to do this again, what I think is a better way to write the series for the square root of x centered at 9 would be to do this. If we take the advice when you take the derivatives literally, and what was my advice was to not simplify, right, your derivatives. Let's take those derivatives again. Your first derivative is 1/2 x. Previously, I wrote -1/2. But how do you get that? You get it's 1/2 minus 1. The next derivative is 1/2 minus 1 times 1/2 minus 2. And then bring that down. 1/2 minus 1, 1/2 minus 2, x to the 1/2 minus 3. What's nice about this is it's a very clear pattern, right? You can tell this pattern is going to keep going forever. Admittedly, there is no easy way to write out the formula other than to just start the multiplication, 1/2, 1/2 minus 1, 1/2 minus 2, dot, 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 and then provide a place where we know where to stop depending on n. Okay, notice you're stopping on n minus 1, right? When n was 4, you're stopping at 1/2 minus 3. So on your nth derivative, you'd be stopping at n minus 1. And then I'm just plugging in 9 for x, so 9 to the 1/2 minus n. Another advantage of this method is, unlike the last one where the pattern had to start at n equals 2, so we had to write the first two terms, this particular pattern started at 1, right? It started at my first derivative, so I can index my series at 1 and only write the 0th term, I guess, which is just f of c, in this case, the square root of 9. I'm not sure WebWorks would recognize this notation, so this maybe wouldn't be the way to go on WebWorks, but if this was a test question or something, I think this is easier. Okay. Yeah, that was my note there. Now for all of those, whichever one you use, I think it's still good practice to use the ratio test would work for all of those methods to find the radius of convergence, which should give you 9. So I would practice that and make sure that you can do that. Now, how do we know it's 9? How do I know it's 9? If you think about what we're doing, we did the center of the square root function at c equals 9, right? Our function is square root of x right here. And the way power series works, power series will do a very good job of modeling your function for every number unless there's a good reason not to. And you can tell that if we're talking about the square root of x and you're at 9, there's only so far you can go, right? You can't take the square root of a negative number. So I can tell that if my center is 9, I could go 9 units to the left before I'm going to run into domain issues. And so if you can go 9 units to the left, you can go 9 units to the right. This series should converge from 0 to 18, which means your radius of convergence would be 9. I would still recommend using the ratio test to confirm that, but that's going to be the answer you're going to get. Okay.